All right, adding vectors. So we learned in the last video that vectors have direction, magnitude, and sense. And now what we can do is apply two vector forces together and find out the resulting vector that comes of it. So for example, here's vector AB, which could also be denoted with the bold letter P, lowercase. And here's vector BC, which can be represented by the lowercase bold vector Q. Either way is alternative notation. We should get used to seeing both. Now, the advantage to the letter notation is we can see that if we go from AB and we add up the force from A to B, then from B to C, we end up with the new vector AC. So as we can see, that actually forms a third side of a triangle, and that third side of the triangle formed by the two vectors does in fact equal the length of the sum, or the new vector that results from the sum of the two. So here's two ways of, we have the geometric representation, add this vector to that vector, and if we line them up from head to tail, we see a new vector as completing the triangle. In algebraic terms, if we add AB vector plus BC vector, we get AC vector. And some clever people might recognize that if it's just sort of like the B's are canceling, and then we squeeze together the A and C. That's not very good mathematical thinking, but in fact that's what's really, that's what it looks like is going on, and that's pretty accurate awareness. Anyway, we could also say that if we add vector P plus vector Q, we get vector R. Now this little tilde on the bottom here is not common. I don't see it very often, but it is in fact an acceptable way to express the same truth that we see. So here's one truth expressed in three unique ways. Now, here's an interesting thing about adding vectors. When we add up our vectors, I'll take this one. As was shown in the last slide, if you take one vector and go from head to tail, and then you line it up with the, I can't remember which one's head or tail. Anyway, if you line them up like this, then when you add a new vector, when you add the two vectors together, it in fact completes the triangle. But here's the thing. It doesn't really matter where these vectors are in space. Their sum is their sum is their sum. Watch, this green vector represents the sum of these two vectors. If I change one of the vectors, it has an influence or an impact on the sum itself. So as you can see, every time I change my initial vector, it has an effect on the sum vector. Here's the beauty part. We could arrange these vectors from head to tail again in space, and then we can see clearly that the green vector is the sum because it completes the triangle. But it doesn't matter how these particular vectors are arranged. We can go from here to here, and that gives us the green vector, or we can go along this first red vector and then go back up in the other direction, and you can see it's still the green vector. So a vector is a force with a direction, and those forces and directions don't have to be lined up on each other, and those forces and directions are still going to add up to some new result. So we can see that in a simplistic way in this fact right here. Here we see vector df. If it is known that vector df is equal to vector bc, then we should be able to conclude that AB plus DF is equal to AC. Here's why. We know that AB plus BC equals AC, and we know that BC and DF are the same. So all we're doing is replacing BC with DF, and it's still the truth, because these vectors are the same. Substitution. So in the picture, we can see that DF is floating off in space all the way over here, and BC is floating off in space over here. But the fact remains that the resulting vector AC can be the result of AB plus DF because those forces are the same. The DF and the BC forces are exactly the same. So let's put this in a little bit of perspective to understand how vector forces really work. We have two different GIFs here. The first one is if a boat shoots across a river and the river has no current, then the boat will go exactly in the direction that it's headed. If, however, the current of the river is being applied to the boat in addition to its direction across the river, then we end up with a new vector. So we have the river vector plus the boat vector added together to create a new vector, which is the resulting direction and heading of the boat. Now, if we talk about an airplane flying, if an airplane has a vector tailwind, then it's going to add to the same direction as the plane, and the plane will get where it's going much, much faster. So we're going to add the two, the wind and the plane speed, together to create a faster vector. And then if we had the opposite, if we have a headwind, then we're going to take away, we're going to subtract the force of the plane, or the wind from the force of the plane, and we get a slower trajectory. And we look at a crosswind, we have a vector going this way plus a vector going down. As we can see, we end up with a new resultant vector, which is a plane shooting off in a different direction than perhaps is intended. So they have to adjust for the wind. So that shows an illustration of why we are interested in adding vectors at all. And you'll notice with the plane, I mentioned subtracting vectors. We're going to subtract the force of the wind from the force of the plane. We can subtract vectors as well. And subtracting vectors is basically adding opposite direction or opposite sense of a vector. So, for example, if we have the force of P plus wind, we end up with this vector right here. But if we have the force of the plane and we subtract the wind, we end up with the new vector F. This new vector F shows us the vector of the actual plane itself, because the plane was heading in this direction with this force, but had the force of the wind knocked against it, and now we're heading off in a different direction at a much slower speed than we were intending. So, put all these ideas together, and here's some simple rudimentary kind of exercises that are designed to get us accustomed to the notation of vectors and the idea of direction and sense and addition of vectors. So here we start with this quadrilateral shown in the picture, OABC. And then we're going to define OA as the lowercase vector a. So here I drew my own picture, and I have lowercase a. And then we also have OB for B and OC for C. So these three lowercase vectors are what's shown. We need to write AC in terms of either A, B, or C. So capital AC, that vector right there, needs to be represented in terms of these three lowercase vectors. So to begin with this, I'm going to look at the vector AC, and here is the vector AC. And to get from A to C, obviously I can travel from A to C, or I need to get somehow the A, B, or C vectors involved in my work. So what I'm going to recognize is here's vector A and here's vector C. If I travel along the road of AO, and then I go to OC, that's going to give me the resultant vector that I want. So here I see vector AC is equal to vector AO plus vector OC. AO plus OC equals AC. And then I'm going to reverse my vector AO with this negative sign right here, and it's still the exact same vector, and then I'm going to add that to OC. And then I recognize that if we take the opposite of OA, that's the opposite of vector A. So we're just going to replace OA with vector A as shown. OC is called vector C, that's given information, that's right here. And therefore, we just use some simple substitution, and then we get C minus A. So in other words, the vector AC shown in this picture right here is a result of the sum of taking vector C, draw that, take vector C, and we're going to add it to the opposite of vector A. So here's vector A in this direction, the opposite of vector A is right here. Boom. And notice, if I take the opposite of vector A, add that to C, boom, we get vector AC, which was the one we were looking for. So I'm looking at my results, and I say my results make sense. It's actually fitting. All right, so we're going to look at BC now. I need to find vector BC. Vector BC is right here. And obviously I can find vector BC by going from B to C, but if I need to involve vectors B and vector C, then I'm going to travel along the path to O. So we've got the first vector appears to be vector BO. That stinks. See what I did there? And then we have vector OC, and if we add vector BO to vector OC, we get vector BC. So that's my first statement right here. BO plus OC equals BC. Put my little vector guys on there. And that's OB in opposite direction. So we could take OB and basically send it in the opposite direction. So that's starting at O in the opposite direction. Right there. Oh, but we took the opposite, so that's the same thing. I'll just reverse that. Having trouble. Okay, so that means then if we take the opposite of B and we add it to C, then we're going to get vector BC. And then here it says take the vector C, there's vector C, and then take the opposite of vector B, which goes right here. That gives us here. And that should be the resulting force, BC. Bam, there it is. Now in the picture you'll notice that this is actually OC, or that's C minus B, which is this vector way down here. But if we look at it the other way, that is, as I drew it before, bam, we still get the same vector. So negative B plus C is the picture shown here, and C minus B is the picture shown here, and either way we still end up with the same truth. Vector BC is the result of C minus B. Alright, the next type of problem here is it says we need to express the midpoint of AB relative to O. So here, the midpoint of AB, here's AB, here's M, which is the midpoint. And we need to actually express the distance from, or sorry, the vector from the O to the midpoint of AB. So in other words, I'm looking for OM. So here we can see in my work, we have vector OM, which is equal to OA and half of AB. So here's OA, and here's half of AB, which takes us to our midpoint. And AB, as we found in the previous slide, AB, oh, we didn't find that. AB is the product of AO plus OB. So AO plus OB is AB, and we want half of that, which is covered right there. And so I'm going to then recognize that AO is actually the opposite of OA, and OB is OB. So we can do some substitution. There's vector A, there's vector B, we have the opposite, and half. And the rest is algebra. I'm going to distribute the 1/2, biggity boom, and that's what I get here. And then we have 1A minus a half of A is a half of A plus a half of B, and then we take out the half, and we get half A plus B. So we might have gotten lost along the way here. I just want to point out that what we've done here is we have expressed the, what did it say here? The midpoint of AB relative to O. The midpoint of AB relative to O, that's OM. We've expressed that midpoint in terms of A, B, and C. So here's half of the sum of A plus B is going to take us to the midpoint. So to illustrate that, what I've done here is actually shown if we take half of A, that would be this vector right here, and if we add that to half of B, which is this vector right here, it takes us directly to the midpoint of AB. And notice my result is a half of A plus B. Here is the vector A right here, added to the vector B right here, and that gives us the long red vector. But I found half of AB, A plus B, is right there. The vector OM is half of the vector A plus B. I don't know if that makes sense to you, but it makes sense to me. Here's what I recognized here. If we take half of a vector and we add it to another half of a vector, that's equal to the half of the sum of the two vectors put together. So it's basically creating a scale model of the triangle, a reduced scale model. by a scalar. So anyway, those are some of the fundamentals then. And again, I'm making sense of it my own way by drawing my own pictures. This is only going to be beneficial if you try to make sense of these questions in your own way, in your own terms. So these questions here are designed to get you just to understand the basics, the notation, the how, the whys, the wherefores. So please spend some time on this. Now, the oh yeah, I was going to do this one too, just a little bit. I just want to show you two things. First of all, the idea that if you look at taking this particular sum, AB plus BC, and you just looked at it in its purest sense, all we'd have to do technically is cancel the b's and say that that's equal to AC. My problem with that is it lacks quality. I mean, it's obviously correct and everything, but if you want to get a better understanding of vectors, we should try to interpret this work geometrically, which is what I did over here. We actually have the vector AB. Here's the vector AB, here's the vector BC, and here's the resultant vector AC. So here is a geometric interpretation there we go. Here's a geometric interpretation of that algebraic interpretation. So I don't want to see anybody doing that cancel thing. You can do it in your mind, but you should make sure that you have a picture to go with it, because the picture is going to make a lot more sense in the long run, because we're working with geometric ideas. And lastly, I just wanted to look at this one. This is CD plus DA. So we got CD plus DA. And then we're going to add that to AB, so to DA plus AB, and then add that to BC. And we end up exactly where we started. Notice C to D, D to A to B, B to C is C to C. So what would we actually write? Well, understand that there is a special kind of vector called the zero vector. That's a vector that has no force or magnitude and no direction. It's just zero vector. And that's what we end up with. We have four opposing forces, and when we add all those forces together, stuck in one spot, not moving anywhere. So, next video is going to talk about some more, well, less than basic applications of what we can know about vectors so far. Just a quick summary, though. We've learned that we can add two vectors together simply by looking at, the sum of the two vectors. It creates a new resultant force. Or we can subtract, which is essentially adding the opposite of a vector. And we recognize that those forces don't have to be any particular location in space. They can just be anywhere, but it sometimes is easier to model or represent or understand when we line up the vectors head to tail. Then we can see their sum more clearly. So that's a practice that we will try to use as much as we can. And there's the algebraic or linguistic, the language part of vectors, and there's the geometric part of vectors, and we should make sure that we strive to bridge the gap, to match that understanding of what we see in representations by symbols compared to what we see in representations by figures or graphs. All right.